Hello everyone, welcome to my video. With relative velocity and relative acceleration on hand, in this video, we will look at most complex motion with everything combined, the motion relative to a rotating axis. Way back to near the beginning of this course, in section 2.8, we introduced these two equations that can be used for non-rotating references. I hope by now you have built a pretty comprehensive knowledge base to realize many problems we deal with were not that simple and frequently requiring us to use a combination of different concepts and equations. For this section, we'll be doing things slightly different. Instead of focusing on how those equations were derived and dump tons of conceptual content on you, I will simply present them and show you how to apply them in problems. However, I will be providing necessary references throughout the video to guide you in case there are some concepts you are interested to learn more about. With non-rotating frame, we have RA equals to RB plus RA relative to B. Oftentimes, this RA relative to B are just being written as a vector R. And this vector R can be broken into X component and Y component and presented as a scalar times unit vector format. And you know this already. Now, looking back at why we replaced RA/B with vector R, this is actually a generalization because the equation we just got can also be used with rotating frames. This RA equals to RB plus XI plus YI. In other words, the same relationship between A and B still holds if you compare the two diagrams on the right. That was the position vector on the previous slide. Once again, we recall from what we know about non-rotating frame when we took a step further to differentiate the position vector to get velocity and then later to get acceleration. In non-rotating frame, when we were taking derivatives of positions to get velocity or velocity to get acceleration, the unit vector was treated as a constant, which was correct because the frame is not rotating. Your I vector is always pointing to the right and J vector is always pointing up. So during the differentiation process, I and J, the unit vectors, were simply kept as it in the equation. They're not changing, they're constant. Now, with rotating frames, since the coordinate system itself is rotating, the direction of I and J is also changing. Although the length is still one unit, they are still unit vectors but for a rotating frame. Therefore, I and J have angular velocity, so they cannot be treated as a constant during the d over dt differentiation. They are not constant anymore. Without going through detailed equation deriving process, here let's look at the end product. The velocity equation can be used to calculate absolute velocity of A in a rotating frame. Here, VB is the absolute velocity of B, omega is the angular velocity of rotating frame xy, small xy, and R is the position vector measured from B to A. We'll talk about that in a moment. And V relative is the velocity of A relative to the frame. Notice here, it's relative to the frame. I didn't say relative to A. It's relative to the frame. Note that we have two frames here. The capital XOY, which is fixed, and the XBY, which is rotating with origin at B. There is a caveat. Point A does not belong to any frame. Does not belongs to XOY, of course, and it does not belong to XBY. They are just set up frames to measure A's movement. Therefore, there are two things here. The point A itself and the underlying frame XBY that A is being measured from. If you can understand what I just said, then let me put a point P here. P is a point on the rotating frame that is coincide with A at that instant. Therefore, when the frame starts to rotate, P is going to rotate with it because P is on the frame. Okay? Now, I want to refine the definition of the last two variables. The position vector R is measured from B to P. P is on the frame. B is the frame's origin. And the relative velocity is the velocity of A relative to the frame xy, which is velocity of A relative to P. Therefore, looking at this equation here, we can replace many parts of it. The rotating speed of the frame omega cross the vector r, which is measuring from B to P, gives us velocity P relative to B. And this relative velocity is essentially VA relative to P. Remember, P is on the frame, or you can even say P is the frame itself. Then this VB plus VP relative to B is actually just the VP here, the absolute velocity of point P, that point, the P point on the frame, or the frame velocity itself. Finally, if I put the non-rotating frame equation here to compare, you can see that the gray highlighted area, VA relative to B, equals to this omega r plus V relative, where when the frame rotates, omega r tells us about the frame rotation effect, and the V relative tells us about the motion within the frame, which is how A moves relative to P. I strongly suggest you pause the video here and to make sure you can digest everything. Here I put the full relative velocity equation on the left. As for the relative acceleration equation, again, I'm not going to do any detailed deriving here. Since both equations share many same variables, I just need to introduce you to the ones that are unique to the acceleration equation. They are the AB, the absolute acceleration of B, omega dot, the angular acceleration of rotating frame xy, and A relative, which is acceleration of A relative to the rotating frame xy. Okay, this should make sense now, because now you should realize A is not the frame itself. A is not on the frame. We have a reference point P. The P point is on the frame. Before we move on to the summary and the example, within the relative acceleration equation, there is something very special. The 2 omega cross V relative has a special name called Coriolis acceleration. This is the apparent acceleration experienced by an object moving within a rotating frame caused by frame's rotation. And this is what makes the moving objects appear to curve relative to the rotating observer. Okay, so if you are interested in this concept, you're welcome to discuss with me further or read the textbook or for more details. This can easily be an entire section or even a chapter on its own, so I'm not going to spend too much time on this to dive into this. But just introducing you to this special term, 2 omega cross V relative. This is a summary page of the equation and its variable you need to solve for any rotating axis problems. Please take notes or screenshots as we will need them for the example coming up. When it comes to solving problems, point A is usually referring to the point of interest. Remember, point A is free to move, does not belong to the frame. When solving problems, I strongly recommend you to use the vector method. It will be extremely tedious. Yes, I just said tedious, but guarantees the correct answer as long as you follow the procedure. Well, the good news is the setting up the reference frame part is usually given. Like the small xy frame will be given in the question most of the time. First, please pause the video to read the question, maybe even twice. Since we have so many variables in this type of question, what we really should do at the beginning is to identify what we need from the problem, i.e., translate the question into parameters and variables. I start with the general equation, VA equals to VB plus omega cross R plus V relative. Then I can see from the diagram, the rotating frame is already set up with the origin at O, and the frame is XDOY, or just XOY here. We are interested in point A, and we want the absolute velocity of A, VA, and V relative, which is the velocity of A relative to the rotating frame. In the question, it says relative to slot AD, which is the frame itself. Since point O is fixed, so we will immediately get rid of VO. We can see there are two unknowns already, VA and V relative in our equation. Let's proceed to see what the question is giving us for the rest. We also know that omega is 2 radians per second clockwise. So we will set omega is essentially the omega OD equals to 2K. Okay, pay attention to this 2K. It's not negative 2K. The reason for this is because how this XY system is set up. Because usually if X should go this way and Y should go this way, and then your Z axis will be coming out from the screen pointing towards you. But in this way, how XY set up, the Z positive direction is going into the screen here. Okay, so that's why we set omega is 2K. And also from the geometry, we would also be able to get the position vector ROA from the geometry. At this instant, you should realize the point A is coinciding with point P, which point P is on the frame and A is free to move. Since A is on OD and AC together, we have looked at OD link already. Let's look at link AC to see what it can offer to us. When AC is rotating, we can use our basic knowledge about rotational motion to get VA also equal to omega AC cross RCA. And where this position vector RCA is a length is already given in the diagram. From the previous slide, we obtained this equation. Now if we combine them by replacing VA, VA is equal to this guy, VA is also equal to this guy. We combine them, we have one big vector equation, two unknowns, where we can use I and J components to find these two unknowns. Totally solvable. This is the sample problem 5/17 in your textbook, and you can verify your final answer there. I strongly suggest you to calculate the final answer for yourself, following the procedure I provided, and verify your answer with your textbook. Given the relative velocity, we can go further to solve the relative acceleration problem. Here, building on the previous question, we now want the angular acceleration of AC and acceleration of A relative to OD. Again, we start with this generic equation here, and then immediately we can get rid of AO because O is fixed, so AO is gone. From the previous example, we already know omega and R. It's the same question, but it is now having an extra part here. Since it's a constant rotation, that means the omega dot part will also be 0 in our equation. And we already obtained the V relative from the previous question as well. For point A, not only we have the relative acceleration equation based on link OD, A also belongs to link AC, as we explained on the previous page. For that, we have a second equation that we can use. The acceleration of A is equal to acceleration of A n part plus acceleration of A t part. And omega AC was already calculated in the previous example, if you remember, and you should. Therefore, we again ending up with two unknowns and one big vector equation that we can solve I and j components by setting up the system of equations. Right? AA equals to AA with two unknowns, A relative and omega AC dot. All rotating axis questions are similar to this. Almost. You need to be patient and carefully identify all the variables. It may seem easy by following with me in the video here, but when you're doing this for yourself, especially at the beginning, it can be extremely painful, and there are a lot of mistakes and traps you can fall into. So make sure you practice more as you can. This recommended reading list concludes this video and chapter 5. Thanks for watching. I'll see you next time.